Welcome back to the CCNP Route Training Series from TrainSignal. Again, my name is Joe Reinhardt. We actually want to consider now the process of enterprise branch operations. Obviously, since more and more remote access technologies have been enabling the workplace, there are a variety of ways of being able to empower branch offices of all sorts of shapes and sizes. In my career, I have designed a number of these types of solutions and actually helped implement them. So we'll look at some of these aspects in this particular lesson. So first, we'll start by looking at branch office access types, different sizes, characteristics, and so forth. Some branch office enabling technologies. These have exploded in recent years. And then finally, we will actually set up a branch office lab with our lab configuration exercises. So first, let's take a little bit of a survey of the different types of branch offices. You might be able to say that one size does not fit all. There are different characteristics. First, we're going to overview the different site types, and then we'll actually break down into a little bit of discussion of each one. Small office, home office, SOHO, telecommuter, small offices, medium offices, and large offices. And we presuppose in this the presence of a headquarters location where most of the information is being sent to and from. There may also be disaster recovery sites, data centers, and so forth, but that's assumed as part of dealing with branch offices. So first, let's take a quick survey of the different types of branch offices and just a little bit of an overview. One size does not fit all. There are some networks that you're going to encounter as a network professional that have sites that are virtually identical. Retail stores, for example. There was a clothing store line I supported back in my AT&T days. Their offices, stores in this case, were virtually identical in terms of infrastructure, in terms of equipment, in terms of the way they functioned, in terms of data flows, virtually identical across the board. There were only minor fluctuations in the differences. There's also coffee shops, and there are a variety of different vendors and types of these sorts of things, but typically they're going to be very, very similar. There's very little variation in the setup. I mean, there may be some as a drive-through, some another doesn't, but the basic setup's going to be similar. Fast food restaurants, for example, McDonald's, Burger King's, other fast food chains are going to be almost identical in terms of the locations where they're doing most of their business. And banks are another example. I did a network audit for a very large bank in the Pacific Northwest, and there was very little difference between just about all of their sites. There were, again, minor variations, but typically across the board almost identical. So these types of networks, there's not going to be a lot of different branch office types. They're going to be pretty much the same. And you might want to subdivide, where there are some minor variations, but this is something to keep in mind. However, most networks that you're going to encounter, design, support, or help operate are going to have sites with varying characteristics. Some of this is going to be based on the physical size of the facility. Is it a 5,000 square foot facility? Is it a 200,000 square foot facility? I mean, a lot of this is going to be different if it's manufacturing and so forth, but the physical size of the facility may be different. Typically, there's going to be a difference in the number of employees that are being supported at that location. The way you support 5 employees and the way you support 20 employees are not going to be exactly identical. And then the type of network infrastructure that's involved. If it's a very small branch, for instance, if you look at the graphic to the right, the small branch may be just one piece of equipment that basically does everything. It may be a Cisco Integrated Services router that instead of having a separate router and a separate switch, there's a module actually placed in that device, and then you would see VLANs and do switch configurations on it as well. Whereas in a medium branch, you might have a router and then separate one or more switches. So this is just an example in terms of the network infrastructure. Something that's not listed here but may also be the case is if you're doing unified communications. If you have Cisco IP phones and a Call Manager Express, or whether it's doing SRST or some of these other things, there may be some variation in the way these sites handle these particular things from an equipment standpoint. Now, most locations can usually be classified on a common set of characteristics. When I did network designs in the various positions I've had over the years, I would usually try to classify at least 5 general types. And again, if there's some variation, that may be helpful, but basic characteristics can be usually broken down into some subset that you can use as a set of examples. And designing and maintaining a number of remote locations can actually be simplified by using these site types. For instance, just again, pictured, we're just using 3 site types in the diagram here, large, medium, and small. But you can define these site types by the type of networking equipment that's in use, printers, workstations, and other devices, not only type but number, the number and types of telecommunication circuits. For instance, you may just have simple analog lines at very small offices, and you may have PRIs, very large telecommunication circuits, at the larger locations. And internet connectivity. Is the internet connectivity is a dedicated internet access over some sort of a serial or Ethernet handoff, or is it more of the broadband consumer types of things? And these are the types of characteristics you can actually use to classify your sites. And in fact, I've done so as a network professional and network architect myself. So here's just an overview of the different site types we're going to look at, just for just a basic general usage. There's the small office, home office, sometimes referred to as SOHO or telecommuter. And many times these are used just about identically. The only difference may be if it's an actual office in an office complex with, let's say, 1 room, or some kind of an executive suite. That could be considered a small office, but not exactly a SOHO office. And telecommuter is usually just the term used for someone that works at home and has, for instance, a home office type of setup. But you'll frequently see these as being almost identical. Then you have the small branch office, medium branch office, large office, and then headquarters locations. And then the basic idea with the graphic to the left, as you can see, the headquarters site, multiple connectivity options, multiple pieces of equipment. The basic idea is there's firewalls, there's data center switches, and there's all sorts of other infrastructure pictured there. But there are a variety of different ways for these types of branches to be connected back to the main headquarters. And that's what we'll consider under the individual site types. So to begin with, as we mentioned, the SOHO or telecommuter. This is typically a single remote worker in a home office environment. And the type of devices that are used there can be very simple. It can be an 800 series router, which can do a great number of things for a home office environment. There's a variety of ways to be able to do that. There's also the Cisco Virtual Office, where the configuration for that device can actually be pushed from the headquarters. It's way beyond the scope of what we're going to talk about, but a very, very helpful enabling technology. The Cisco 1900 series router can also do a lot for the small office if there's a little bit more that needs to be done and some more capabilities. And it could also be supported using an ASA 5505, which has been used over the years to build point-to-point tunnels. The technologies that are typically supported in this small branch or SOHO branch, home worker, unified communications, where Cisco IP phone can actually be sent across an internet connection using secure tunneling. Wireless can be supported. And then obviously LAN and WAN using Cisco IPsec from the remote site router to the headquarters router. And typically for this type of environment, you're going to have broadband connectivity, which we'll actually get into shortly, but cable, DSL, wireless internet, and some other options that are available. The network functions that are typically required for a SOHO or telecommuter environment is usually PPPoE, point-to-point protocol over Ethernet. Another variation is PPPoA, PPP over ATM, which is typically for DSL. Usually there's some type of authentication mechanism that's used. There's network address translation, typically port address translation. Virtual private network, DHCP. There's usually going to be an integrated switch in the device that's in use. VLANs, 802.11, which is wireless. QoS. And some of these are not required, but they may be something that would be a good idea. Obviously, you want a firewall or packet filtering, and then usually there's some kind of static or default routing back to the headquarters. Notice in the graphic to the left, you have a single device that's pretty much integrating all of the functions. They're building a site-to-site tunnel across the internet and using a secure environment with IPsec and encryption and those sorts of things. And usually there's some sort of broadband internet that's involved there. So the small branch office, the graphic we're using is the same here, but this is slightly different than just the SOHO or telecommuter type of environment. This is typically less than 50 workers in a single physical location. A small office, for example. It could be just several rooms and so forth. It's usually going to involve a single router, but it may involve one or more switches. A lot of Cisco switches have 48 port count And so obviously if there's 50 workers versus 44 or 48, for example, you may require more than one switch to be able to accommodate those additional users, as well as printers and other mechanisms and devices that may be operational there. Usually this is going to involve a 1900 series router because the capabilities that it has are greater, or maybe even a 2900 series depending on the requirements. An AOSA 5505 or 5510 may also be a possibility. I've actually designed this for a number of customers as well. And the technology supported, obviously unified communications. You could wireless LAN WAN with IPsec. You may have broadband connectivity to the internet, or it may be dedicated internet access. This could be in the form of a T1, it could be some sort of an Ethernet handoff, but this is typically a more dedicated circuit from a service provider. The network functions required, PBPoE or PBPoA, we talked about before, NAT, VPNs, DHCP, because the remote locations may want to actually have DHCP supplied by the router device that's there. Firewall packet filtering, split tunneling, meaning internet access goes directly out from the branch site out to the internet, but secure traffic is sent through a secure tunnel back to the headquarters. And in this case, you may want to use GRE for routing protocol support. For instance, maybe EIGRP or OSPF across the tunnel, which is possible when you use GRE configurations. The medium branch office, obviously much larger. If you looked at the graphic to the left, now we actually have a higher level of connectivity that we're looking at. Probably a primary WAN circuit back on using some type of service provider service, and perhaps a secondary circuit that uses not just local internet access, but also uses a VPN tunnel as backup. And again, this is something I've designed a number of times where it's an inexpensive way to be able to create a backup connection, but also keeps bandwidth conservation because the internet is being serviced locally. So this could be from 50 to 100 workers in a single physical location. It could be a number of offices, perhaps even an office park. But usually it's still going to involve a single router, but it's obviously going to involve one or more switches. And by one or more switches, if it's a chassis-based switch, such as the 4500 or 6500 series, then obviously you would be using one switch. But if it's stackables, then it's obviously going to be multiples. You're looking here at a 2900 or 3900 series router. And again, there's going to be perhaps unified communications, wireless LAN, WAN, a number of different workstations and sort of things that are supported. Connectivity, there may be some sort of private WAN circuit. When I worked at AT&T, these were becoming very popular. And instead of there just being broadband, it may be dedicated internet access. Doesn't have to be, but it may be. Obviously, with the types of network functionality, you're going to need dual connectivity, a circuit back to the private network, a circuit to the internet network. Being able to support VPNs, NATs, firewall packet filtering, GRE for routing protocol support, and very likely some type of routing protocol will be used in this environment because, for example, the private WAN circuit could be weighted as more preferable, and the internet circuit using a VPN would be more preferable if there was a failure on the primary circuit. So routing protocols can actually create a lot of business continuity in this particular case. The large branch office. This is somewhere between 100 to 240 workers in a single facility, although it could be a campus type of location. Obviously, when you start getting to this number of workers, there could be a variety of separate buildings that may be involved. So this type of equipment is going to involve frequently dual routers, not just one, but in case of the failure of one device, another can take over. So we're looking here at a 2900 or 3900 series router, typically more high-end. Again, using unified communications, wireless LAN, WAN, in this case dual connectivity. If you look at the graphic, you have obviously multiple switches, but you have dual connections to the internet and you have dual connections to the private WAN. And there are a variety of ways to be able to program this to, again, ensure business continuity. Obviously, with large branch offices, you're looking at dual connectivity of some type, one set of circuits to the private WAN, other set of circuits requiring dedicated internet access. But again, this dual connectivity with dual devices makes business continuity at that particular branch a lot more likely. Obviously, network functions, dual connectivity. This is going to be multiple interfaces. VPNs, NAT, firewall. In some cases, instead of there being a separate internet circuit, it could be that there'll just be multiple private WAN circuits, and internet may be served out of the central location, but frequently there are internet access at the individual locations. split tunneling, GRE, and again, routing protocol support for the multiple connectivity options back to the headquarters. Obviously, having considered the different sizes and types of branch offices that we talked about, there are also a variety of technologies that enable branch offices to function at their fullest capacity. So we want to look a little bit at these technologies, and they're going to involve broadband internet access in many cases. In some cases, private wide area networks, Cisco integrated services routers to some substantial degree, and then virtual private networks. So to begin with, I created this sort of eye chart slide as just a quick overview of the different types of broadband internet access options that are available. I'm obviously looking at this from a US standpoint, but there are a number of options also available globally in the different regions of the world. But there are a number of primary types of connections that are the most desirable, and then there's some more what I would call legacy environments. For instance, ISDN is going to be in many cases a legacy type of connection that isn't going to be able to give you as much as you'd want. You can see here the types of connectivity, the transport that's involved, the type of provider, frequently typical speeds, and this is one of those things where I could use the phrase your mileage may vary because there are a variety of factors that affect it. Protocol that's being used, the method of authentication, and then some caveats, and we'll actually look at each one of these to some degree. Begin with, one of the most popular technologies that's used is called DSL, or Digital Subscriber Line. And the idea behind DSL is that an analog phone line only uses a tiny amount of the available bandwidth to transmit voice. If you remember, voice typically is going to be about 64K. That's a whole discussion with the Cisco Unified Communications Suite, but that's pretty much the point, is you see the frequencies, the analog frequencies that are being used, and it's a very small amount of the bandwidth. There's a great deal of unused bandwidth on that particular circuit that could be used for carrying data. So being able to multiplex voice and data across a copper telephone line is basically what DSL was born to do. This creates the ability to be able to transmit high amounts of data across standard analog copper lines. Now, there are some newer technologies where there's actual fiber connectivity to homes, but this is just the basic technology using the analog phone lines. It uses, again, the unused frequencies to carry data along with the voice. Usually there's some kind of a splitter or a filter to keep the line noise from the data bleeding over into the voice. It almost has this sort of snowy sound. And what it actually uses is something called ATM, which back not too many years ago was a popular networking, wide area networking technology. It stands for asynchronous transfer mode. And typically this is used at the telephone company's central office using a device called a DSLAM. You notice it's pictured here to the left. And I want to comment here on the DSL modem that's pictured in the middle. Now, if you really want to get overly technical, modem stands for modulator demodulator and is actually related to the days of dial-up. But the function ends up being referred to as a modem. So you'll have a cable modem or a DSL modem. It's not really a modem in the strictest sense of the word, but it's a basic term that's used for it. So the DSL modem actually creates a signal, an ATM circuit signal back to the DSLAM, and then it's then carried out to the internet on the service provider's network. Usually there's some kind of authentication that requires performance in order to be able to enable or prevent unauthorized use, and that's what PPP over ATM or PPPoA is all about. And the speeds can range from, and I have here 768K to 7 megs. This is usually distance dependent, but there are a lot of factors dealing with service providers and distance and availability and those sorts of things. So there are a number of different types of DSL, and this is certainly not exhaustive, but there's a number of them. And there's ADSL, which is asynchronous DSL, and a very popular method. Usually means that the upload and download rates are different. There's SDSL, or synchronous DSL. There's a service provider named Covad that popularized this a number of years ago. IDSL, which is an ISDN-based DSL, and the main reason for that one being in existence is because of the distance issues. Then there's VDSL, or very high rate DSL, and so forth. There's a lot of different ones. The primary drawback of DSL is distance from the telephone company central office. The further away you are, the lower speed you're going to get. I actually lived in an area where the telephone company central office was a significant distance away from my home, and I was incapable of getting DSL because the distance was too great. So keep in mind that your availability is going to be affected by the distance from the central office as well as available speeds. The closer, obviously, the greater speed you can get. Cable internet is another technology that's very popular, and this provides high-speed access over the same coaxial cable that's already delivering television circuits. Usually within the service provider network, there's something called HFC, hybrid fiber coax, and there are a number of different service providers, Comcast being one, that provide this type of service. And pretty much it's the same idea of when you dial into different channels, so to speak, on a television, it's just that internet is being delivered on a different channel, if you will. So that's the basic methodology there. The standard that's being used is called DOCSIS, which stands for Data Over Cable Service Interface Specification. DOCSIS. And there are a number of versions available. I believe currently in 2011, version 4 is the most current. It uses PBP over Ethernet. Again, you see the terminal device, the end user, cable modem, and then the cable modem termination system. It's a DOCSIS device that's doing all of these different things. Speeds can range from 4 to 6 megs or more depending on location, availability, and so forth. There are no issues of distance from the service provider. That's not an issue at all because of the way the technology works. But just as when many users on a local area network are using the network, it could slow things down. It's the same type of idea. The more users within a neighborhood would maybe downloading or streaming movies or things like that can potentially degrade the quality or speed of the connection. Now, as a person that actually uses cable modem technologies, I've never noticed a problem, but it is a possibility. Something else that's become more popular in recent years are different wireless mechanisms to be able to access the internet. And I'm not talking about 802.11 Wi-Fi type of access, but rather different technologies that are used over a cellular type of connection is what they're typically called. There are usually two flavors. They're sometimes called 3G and 4G. And the whole idea is that they create and provide high-speed access over the wireless media. It can be to an individual computer, as is actually pictured here in the graphic to the left, or it can be to a device that supports that, a router or a modem, if you will. But this uses specific radio types. 3G uses typically CDMA or EVDO, and the 4G is typically what's referred to as WiMAX. And WiMAX uses a completely different set of technologies. It's 802.10 designation, but there are some others as well. End-user authentication is typically going to use EAP, Extensible Authentication Protocol, aka and other methods. There may be some sort of PPP variant that's used. Speeds can range from 350K to 7 megs, and there are a variety of factors that can affect speed. The quality of the connection, are there interference elements, is it line of sight, and so forth and so on. And the primary drawback obviously is going to be availability. For instance, you can get 3G in many, many places. At 4G, it can be a lot more selective and spotty. And then obviously, because it's a wireless medium, radio interference can be a factor. So another branch office enabling technology is private WAN networks. And again, I spent 5.5 years of my career at AT&T and was involved in designing, building, and promoting wide area networks of various types. So there are a number of different types. One that goes way back to the mainframe days is private line access. And this provides point-to-point connectivity. You can use any type of protocol. You essentially own the circuit end-to-end. If you wanted to use ATM's encapsulation, you could. I don't know why you'd want to, but you'd have that option. If you wanted to use something completely different, you could. It gives you full bandwidth at all times with the lowest latency. I actually designed around an issue where there was a company whose headquarters was based in Hong Kong, and the MPLS circuit that we sold them was going to have too much latency just because of the distance and so forth. So we actually used a private line as an alternative circuit that went into that particular device as well in order to be able to compensate for the latency issues. And it had to do with a customer resource management package that they were using. You don't have to use authentication mechanisms because you own the circuit end to end. You can have reigns of fractional T1, in other words, less than 1.544 megabits per second to 10 gigabits per second or more, depending on the type of service or technology. Some handoffs are going to be more telecommunication type circuits, traditional stuff. Others are going to involve maybe Ethernet handoffs, so you don't have to buy expensive adapters. Usually the drawback with private line technologies is going to deal with cost and unused bandwidth because it's a per mile cost. A T1, for example, between one building to another a quarter mile apart and the one a country apart are going to have vastly different costs. And unused bandwidth. If at night you're not doing a lot of data backups, then the bandwidth's essentially being unused and you're paying for a lot of bandwidth you're not using. So that gave birth to what's called shared services. Instead of there being a point-to-point connection, physical connection, you actually use virtual connections. This provides not just physical connectivity, but logical connectivity. Usually this means that there's only going to be certain types of protocols allowed. Frequently it's just going to be IP-based. It gives you amounts of bandwidth according to a service level that's shared by customers. If one customer is hogging a lot of bandwidth, it could affect another customer. And there are a variety of mechanisms in service provider environments to keep this from happening, but it is still a possibility because it's a shared network medium. You don't usually need authentication mechanisms, and the speeds again can vary, T1 and up. There can be Ethernet handoffs and so forth. Usually the drawback is increased latency and less overall performance. It's not enormous depending on how it's designed, but it could be done and could happen. So these are usually provided by some sort of telecommunications providers, AT&T, Verizon, and so forth. So just the types of services. First, obviously what I would call legacy services, frame relay and ATM, very much being phased out and in favor of other things. The currently available circuits are private IP WANs where a section of the service provider's actual IP network is reserved for private connectivity, not internet connectivity. Then it's obviously just MPLS or multi-protocol label switching, and then there's Metropolitan Ethernet types of services. The benefits of these is you can do quality of service, you can have bundled internet access many times, one circuit doing more than one thing, and obviously you still have lower cost but higher reliability because they're telco type of circuits. Another branch office enabling technology has to do with the Cisco Integrated Services Routers. These came out a number of years ago with the 1800, 2800, and 3800 series routers, sometimes referred to Generation 1 or G1. The newer line is the G2s, and typically they have much greater power, much greater capability, are more video ready, and so forth. We want to just do a quick survey of the types of devices. First, there's the 800 series integrated services routers. They're usually small desktop form factors. These are targeted at the SOHO or telecommuter type of environment where there's one or a handful of users. It gives you power over Ethernet support if you need to support access points, wireless access points, or IP phones, obviously IPsec-based VPNs, and there are a variety of WAN interfaces available, from DSL to broadband using Ethernet handoff and so forth. The 1900 series, rack mount form factor, typically 2 rack units. It's more of a high-end telecommuter if there are some heavy needs, or the small branch office. There are multiple interface cards available, and IPsec VPN support, very, very important. The 2900 series, again, rack mounted. It can be 1 or 2 RUs depending on the model, because there's, for instance, the 2901, the 2911, the 2921, and the 2951, all with different capabilities, slots, and services provided. It's usually going to be used in more of the medium branch office. Again, multiple interface cards, IPsec VPN support. In many of these devices, you can actually put switch modules in one of the service module slots to be able to actually do everything in one device. Then there's the 3900 series. It's basically a 3 RU unit. It's typically for large branch offices and also headquarters locations. You're going to often see 3900 or ASR 1000s, which is an entirely different discussion. Multiple interface cards, VPN support, a lot of very high-end protocols supported through these devices. The different types of services that these integrated services routers support are pretty vast. They're going to support DHCP, both as client and as server. As client, doing PPPoE or PPP over ATM, for example, in order to be able to have authentication provided to the service provider network, as well as being able to provide DHCP to devices on the network. In other words, just being able to plug a laptop PC, a handset, all sorts of other things. And it's even possible to use DHCP relay. In other words, if the headquarters location wants to actually control all DHCP allocation, the device can actually relay that to the headquarters. I worked with a company that had about 800 remote nodes and actually preferred to operate that way, relay versus actually having an on-site server. Network address translation is another factor that these and support that these devices are going to bring. It's usually going to be port address translation, which means a single IP address to whatever services are located behind the NAT boundary. And obviously, if there's specific things that need to be mapped, you can do that using static mapping. In fact, the lab that we have set up, I have a very extensive list of static mappings created in order to be able to easily access the devices that we configure in our lab exercises. And then obviously GRE tunneling, which allows dynamic routing from the headquarters. We configured this in one of our previous labs. And it can be paired with IPsec-based VPN to support both routing protocols and secure encryption. Wireless is another thing that can be supported either natively. For instance, in the 800 series, there are devices that automatically have it enabled. It can also be an external access point. Because of that, there's Power over Ethernet available, internal controller modules, and it can actually extend wireless, enterprise wireless, to that particular branch where the main controller is located elsewhere, but it's still part of an overall wireless environment. Unified communications, obviously Cisco IP phone support, voice and data VLAN separation, which is very, very critical. SRST, which is survivable remote site telephony, meaning that if the communications manager system goes down, the link is severed between the branch office and the headquarters, the phones can still function. And then there's something called SRSV, Survivable Remote Site Voice Messaging, which enables a local server located within the router to be able to take over as well. And there's also enhanced SRST, which can actually make the device operate very much like Communications Manager. And obviously security as well, firewall capabilities and IPsec VPN tunnels back to the headquarters. Virtual private networks, another very, very important enabling technology for branches, because obviously in many cases, instead of there being a private WAN circuit, it's being built over the VPN, over the internet. And this can be done, first of all, with site-to-site. Site-to-site means that one device is creating an encrypted connection to another device. And this can be point-to-point, much like the GRE tunnels that we talked about, or multi-point. There's dynamic multi-point VPN. For instance, in the graphic to the left, what's being depicted here are point-to-point tunnels between the remote locations and the headquarters. What DMVPN does is it allows dynamic creation of spoke connections where all the remote connections would be able to communicate to each other directly as well. That's DMVPN, or dynamic multi-point VPN. It can utilize pre-shared keys, which is frequently how VPNs are configured, but it can also use digital certificates, or PKI, and you can use a virtual tunnel interface on the router to be able to create some of these things. It utilizes the internet per transport, and if you use IPsec, it encrypts the traffic using one of several mechanisms, DES, triple DES, and AES, for example. And typically these are built between devices and physical locations rather than end users and the headquarters. Remote access VPNs are contrasted from site-to-site VPNs in that they're not from one site to another, but from a user back to a headquarters locations. Point-to-point tunnels for connectivity, again, pre-shared keys, we talked about this just a moment ago. Internet for transport, encryption, it's built between users and the headquarters. And it can be done through standard IPsec tunnels, or there is a technology called AnyConnect, which utilizes an SSL-based VPN as well. Configuring a site-to-site VPN is fairly straightforward, though there are definitely several moving parts to it. First, you have to define the traffic to be encrypted. You create an extended access list. In other words, traffic going from one source to one destination, identifying that traffic. Then you define the security policies using the crypto IPsec transform set command. We'll illustrate this later. You define the ISACAMP policy using the crypto ISACAMP policy command. Then you create what's called a crypto map. an encryption map, but in iOS it's called a crypto map. And it ties all of these separate elements together. You usually name the encryption map. You identify the transform set, which is just basically the type of encryption you'll be doing. You set the VPN peer, in other words, what's at the other end of the connection. And then you identify the access list created earlier for the source and destination traffic in order to be able to properly create that. And then you apply that to an interface. For instance, in the headquarters router that's pictured here, it would be whatever internet-facing interface that is. You can verify VPN functionality with a couple of commands: show crypto session, show crypto engine connections active, which I've used many times. You can actually do a ping and then see how it's incrementing. Show crypto ISACAMP peers, show access lists, show crypto IPsec SA, and SA stands for Security Associations, which is what's created. So now we actually want to create the PPPoE configuration on the branch office router. And as we've talked about before, we've already created the configuration here. So if we do a show run, we'll look at a couple of things here. First of all, you can see that different ranges of the DHCP ranges have been configured here. Now notice here there's one for data, one for voice, lists all the things that you would expect. One thing that's different with the voice is it's option 150 10.11.11. This actually specifies where the TFTP server is located. And notice here on our Fast Ethernet 00 interface, there's nothing configured. Notice here, it's indicating VLAN 100 on these interfaces, which is the voice VLAN. It's the voice VLAN command. The data VLAN is VLAN 1, which is the default, which is why you're not seeing anything else here. Notice here, VLAN 1, the range we talked about, and VLAN 100, which is our voice. You can see the NAT statements as well. Now what we're going to do is we're going to configure our PPPoE configuration. So we'll start with here. There's a couple things I want to draw your attention to. Notice here it's saying PPPoE enable client group global. This is allowing PPPoE on the interface, and it's also indicating the dial interface, which we'll reference down here. So we'll start with the physical interface configuration. Copy. So we have that done. We have our dialer interface. And notice here you can see a number of different things. You can see the dialer pool, dialer group. Dialer interfaces are more familiar for those of you that may have been doing configurations for a long time. But here's some things that are important. We're listing our username, our password, and then we're also listing that the default route will be out this particular interface. So let's go ahead and got all that in. Now notice it's showing that the interfaces is up now. So let's do show IP interface brief. Now look, dialer interface has received everything by PPPoE. Now we could do ping 10.222.222.2 because I happen to know that that's the default router. And now let's see if we can ping other things, 10.5.5.5, to see if it's able to reach the other parts of our lab. And it has. So you can see very easily how the PPPoE configuration is created. We've already got this default routing here, but let's just go ahead and make sure. Copy. If we do show IP route, see our gateway of last resort it says directly connected, dialer 1, because that's where it's learned it from. And so that's pretty much the sum total of being able to configure the PPP over Ethernet configuration. So you have your physical interface configuration and your dialer interface configuration and a default route pointing out. Now we actually want to go through the process of configuring a VPN across two routers in our lab. We've actually chosen router 5 and router 9. And as we had reviewed before, there are a number of different steps involved. You notice here we first have highlighted you have to define what traffic is going to be encrypted. We're suggesting that we're going to encrypt traffic from the VLAN 5 interface to the VLAN 9 interface on router 5 and router 9 respectively. We're also going to define our policy. We're going to be doing a pre-shared key and Diffie-Hellman group 2. And we're not going to go through and define every single one of these. We're just giving you the basics of how to configure one of these. The next thing we do is we actually define the key that we talked about above, and then we set the peer address. We're actually going to use the outgoing interface FA0/0.79 on router 9 and FA0/0.25 on router 5. Where they're going to specify we're going to use triple DES, doing what's with our transform set. Then we actually define our crypto map, which is most of where these things come together. The peer address, the transform set, which matches back up here, and then the access list that we talked about, and then we apply that to an interface. So we'll actually do that now in router 5 first. Configure terminal. Configure terminal. First, let's paste our access list in, identifying our traffic. Then we will put most of our crypto configuration in. Then we will create our crypto map. And finally, we will apply it to an interface. So the traffic coming in and out of this interface will be examined and matched to the access list to decide whether or not traffic will be encrypted. And notice now it says that the process is now on, because all the elements are there for configuration. So if we did show crypto engine connections active, you can see that it's been set up, but nothing's happening yet because we haven't sent any traffic across. So now we will go to router 9, and we will repeat the process, obviously in reverse, because now we're listing the source as 192.168.9.0 and the destination as 192.168.5.0. It was reversed before. So we apply the access list. Well, we configured the access list. We actually apply it later. We have our basic crypto configuration. Then we apply it to an interface, obviously then facing back in the other direction. Do a right mem there, and a right mem there. Now we do our show crypto engine connections active again, but this time we're going to ping. Now I want to show you an important reason why you have to identify this correctly. First we'll just do ping 192.168.9.9. No problem. But if we do the show crypto engine connections active, notice nothing's happened, because remember, the source has to be matching that access list as well as the destination. In this case, the destination was matched, but the source was not. So let's do an extended ping. 192.168.9.9. And it asks, obviously, several other things. This time we want to specify the outgoing interface, so we'll make it 192.168.5.5. because then it will match our access list configuration. We go through the rest of it. Now notice the first packet timed out, but then the rest of these, 4 of them to be specific, have actually passed through the IPsec tunnel that we've configured. Now notice what's important here. We had 4 successful pings, and notice that 4 were encrypted in one direction. In this case, this was decrypted coming back. This is encrypted being sent out. IKE stands for Internet Key Exchange. That's one of the initial processes. And IPsec is our actual encryption. If we were to do another ping, back to the target interface. This time the tunnel's already been set up, so there won't be any timeouts. Notice here, there's 5 actually here. So 5 and 4 is 9. Actually, I wasn't intending to telnet to it, but we can do the show crypto engine connections active command again. You see now 9 packets encrypted and 9 packets decrypted, just because we put these other 5 pings going through. So that's one way of being able to verify that it's working correctly. You can do also show crypto IPsec. See, you'll have some options here. And let's do security associations. Notice now we have, notice the peers, local and remote. You can see things that have been encrypted. This shows you the other side, the peer essentially for that. And that's the basics of employing a site-to-site VPN using IPsec. Now, to verify some of the lab exercises that we'd created, and we actually did some of these, there are several aspects that you have to use to be able to verify. First, you have to confirm the upstream connectivity to make sure the PPPoE, for instance, worked correctly, and we were able to do that. We did the show IP route command, showed that the default route was pointing to the functional dialer interface. And then, obviously, we used ping and trace route to be able to make sure that what was there was, in fact, correct. In this case, it was 10.222.222.2, which was the upstream router. We used R1 as our PPPoE server. So if we had wanted to, we could have confirmed NAT functionality by pinging from one of the inside addresses to the outside addresses, and you would have seen an increment when you do show IPNAT translation. Once we'd configured our VPN, as we did a moment ago, the easiest way was to be able to ping, in this case, router 7 or router 9's VPN interfaces. And we were able to use the show crypto engine connections active to be able to see, in fact, that the counters had incremented correctly. If you recall, the first time we sent pings, the first one failed, the 4 following were successful. Then we did another extended ping, and that made a total of 9, which we were able to see in the counters. So some terms to know. Broadband is obviously this umbrella term used to describe high bandwidth connections to the internet. DSL is digital subscriber line. This is a very popular broadband technology, typically given out by phone companies to provide data and voice on the same copper phone line. There is something called a dry DSL line where you do not have to actually have voice service from the phone company to get. PPPoE is the point-to-point protocol over Ethernet. This is an authentication mechanism used by service providers to ensure verifications of those accessing their networks. Otherwise, anybody that had physical access to your phone line would be able to, in fact, have access to your internet. VPN is virtual private network. This is the use of security mechanisms, for instance, IPsec, to ensure privacy across public connections, namely across the internet. Site-to-site is one type of VPN, typically used between network devices, routers, and firewalls to create a point-to-point, or in some cases a multi-point connection between locations. And then there's remote access VPN. This is a type of VPN typically used by remote workers. So we've covered a lot of material in this lesson. We've first talked about branch office access types, SOHO telecommuters, small, medium, and large offices, the ISR Generation 2 routers, the 1900, the 2900, the 3900, and the 800 series. Branch office enabling technologies, broadband internet, for example, PPPoE to be able to authenticate connections. And then finally, we covered our branch office lab configuration exercises, where we actually authenticated using PPPoE and used a site-to-site VPN between 2 of the routers in our networks. Thank you for your kind attention, and we'll have more to share with you later.